Hi, I'm Beth Faber of the Hydrologic Engineering Center, and this is the second video of Lecture 2.3 on incorporating uncertainty into the computation of expected annual damage. In this section, we're talking about Monte Carlo simulation. So this is the second in our list of topics. So Monte Carlo simulation, yes, is named after the city of Monte Carlo. They do a lot of gambling there, and a lot of probability theory and examples revolve around gambling. There's a lot of money in it, and so there's a lot of interest. So Monte Carlo methods are methods that use random numbers to evaluate questions and problems. There's a lot of uses for Monte Carlo simulation. I'm going to describe it as a method for evaluating a function of a random variable. Random variable is represented by a probability distribution, and it can be hard to drag a probability distribution through some function, be it an equation or maybe an entire analysis process that includes modeling and other methods. So what we're going to do is replace a probability distribution of a random variable with a very large sample of values from that distribution, and then we'll use each member of the sample in computation. Right? The idea is that it's a lot easier to do math on a member of a sample than it is on the probability distribution itself, especially if that math involves deterministic modeling, for an example. Right? So the result of this computation on all the sample members is that now we have a new sample of the output of the function, and we can use that sample of the output to infer its probability distribution. This analysis process can work on any number of random variables, and therefore any number of probability distributions. We can have 1 or 2 or 10 or 100 distributions being evaluated with no added complexity. So let's run through this. We're interested in some variable y, which is a complex function of another variable x. So at the risk of introducing some confusion in how the FDA software works, I'm going to call random variable y damage. I'm going to call variable x stream flow. This isn't how the FDA software does this. And when we get to talking about how that works, I'll remind you that it's different than we're talking about now. But for the moment, variable y, our output, is going to be damage, and variable x, our input, is going to be stream flow, and variable y is some complex function of variable x. So our variable x in this case is a random variable, and it's described by a probability distribution. So here's our distribution. Might have some equation to define it. If x is a random variable, that means y is also a random variable with a probability distribution. Now, it can be pretty hard to drag a probability distribution like this through this complex function of x, right? That complex function might be the deterministic modeling, and it might be just summary relationships, but either way, it'll be hard to pull this through. So rather than attempt to do that, we're going to use Monte Carlo simulation, right, to determine the distribution of y. The first step is to replace our random variable x and its distribution by a very large sample of values from the distribution of x. So this histogram represents the very large sample of values. Now, this is kind of the opposite of what we did in the last lecture. In the last lecture, we looked at estimating a probability distribution from a random sample, and we said that as the sample got very large, the estimate of the probability distribution would get very good. But what we're doing here is the opposite. We're starting with a probability distribution, and we're randomly generating this large sample of values for the purpose of replacing the probability distribution. So we're going in the other direction. Right? So we've generated a large sample of values of x. Now, for every member of the sample, we're going to compute damage, y, as the complex function of x, be it the deterministic modeling or reflecting through summary relationships, or however it is that we're going to compute damage. That's going to give us a very large sample of values of our output y. Right? Here's our large sample of our output y, our damages, and from this sample, we can infer the probability distribution of y. Now, this is going in the direction of what we did in the last lecture. Right? We have a sample of values from which we estimate the probability distribution. Now, an important thing to note is that Monte Carlo simulation doesn't add any information to this process at all. All it does is it integrates the information that we start with by defining our variables and their probability distributions. So back here, we might have seen some very large values of stream flow. That doesn't mean those values of flow are possible, Right here, they've been sampled just to flesh out the probability distribution that we defined. And if that probability distribution isn't accurate, then these values of flow might not be possible, right? But they're here in the analysis because of the input distribution that we defined, right? So these large values of flow and the large values of damages that they might produce in the computation, right, are not necessarily true, and they're not new data in the analysis. They're just a reflection of the probability distributions we assumed, right? So no information comes from the Monte Carlo, right? So let's consider, instead of just one input variable, maybe we have two input variables. So variable y, damage, can be a function of two random variables, x and z. Maybe x is still stream flow, and z is the starting level of a reservoir that's above our damage site. So the lower the reservoir, the more empty space and the more water it can hold back in a flood event, and therefore the less damage. So let's create a random sample of variable x, and then we just also create a random sample of variable z. We take one member from each sample, and we can then still compute variable y as the function of both of those. Right? So we still get a large sample of our random variable y, our output damage. Right? It doesn't matter how many input variables I might have had, I would have just created a sample for each of them and used them in my function for the output. Okay? So here I'm assuming that stream flow and reservoir level are independent and sampling them independently, but maybe they're related. Right? Maybe the watershed is completely saturated, and so we have higher flow, and the reservoir is already full, or as full as it's allowed to be, right? So maybe they vary together. And if they do vary together, if they're correlated, then we can maintain that correlation with correlated random sampling within the Monte Carlo simulation, right? So in this example, both of our random variable inputs were natural variabilities. Stream flow, reservoir level, both vary randomly in time. But we can also do this approach with knowledge uncertainties, right? So let's say our random variable x is Manning's n, channel roughness. So that's a knowledge uncertainty and can be represented by a probability distribution showing the likely values of Manning's n. And maybe my output, my random variable y, will be the stage for a given flow. And I would compute that stage with a hydraulic model. Okay? So if I replace my distribution of Manning's n with a large sample of values, then I would run my hydraulic model for every one of those sample of values and compute the stage for my given flow, right? And that's going to produce for me a sample and then a distribution of that stage for a given flow. Right, so if you think back to our rating curve, one of our second summary relationship of flow versus stage, if you remember, we had a PDF of uncertainty around stage for a given flow. So this analysis can help us determine that distribution, right? So we've just transformed Manning's n and its distribution into the distribution of stage for the specified flow. Another possibility is that instead of computing the distribution of stage for a given flow, we can reintroduce flow as a random variable z, right? So we bring it back in as a natural variability, and now for every sample member of Manning's n, variable x, and every flow, variable z, I can compute my new output y damage, right? So now damage is a function of both Manning's n and flow. And I've computed my damage frequency curve with both a natural variability and a knowledge uncertainty considered. Now, usually we actually don't put our natural variabilities and our knowledge uncertainties into the analysis at the same time. We want to evaluate them separately and see their separate impacts on our decision metrics, but it is possible to consider them together. So let's move on to how we generate the random sample, right? Where do we get this large sample of values? The first thing we do is we switch from the PDF form of our probability distribution to the CDF form, or cumulative form of the distribution, right? Next, we're going to generate random values that are uniformly distributed between 0 and 1. Right? Random number generators or pseudo-random number generators usually produce a 0, 1 value. If you remember in our workshop in which we had Excel roll a six-sided die for us, we started with the rand function that produced a uniform 0 to 1 value. Right? And then we're going to use that value as the cumulative probability on the vertical axis of our CDF. So I like to show this visually. We're going to take each of the uniform values, put it on our vertical axis as a cumulative probability, reflect it through the curve and down to get a value of x. All right, we're going to take the next one, reflect it through the curve down for another value of x, and then another, and another, and another, and then another. Right? So our probability values are going to be spread uniformly across this vertical axis because by definition we're using a uniform random variable, but the x values are not going to be spread uniformly, right? Unless the CDF is a straight line, but in most cases it's not. So our x values are in fact going to be clumped fairly closely together where the curve is steep, right? Where the curve is steep, we're taking a wide range of the probability and condensing it into a narrower range of x. And then when the curve is flatter, we're taking a narrow range of probability and spreading it across a wider range of x on the top and on the bottom. So you can imagine this sample of x's, if we were to do a frequency analysis on it and make a histogram, then we're going to see more values in the middle and fewer out of the tails. And in fact, it's going to look like that bell curve PDF of the normal distribution that we saw on the last slide. Right? And that was our intention, to replicate that probability distribution, right? So this has worked out. Right? Next, we consider how large a sample do we need, right? Sample's large enough if it can reproduce the probability distribution. One example is that we will compute the correct distribution parameters from our sample estimators, for example, the mean and the standard deviation. Right? So what kind of a sample is this? Right? If you think back to the last lecture, and I can't actually hear your answers, but I'm imagining somebody saying a representative sample. Right, that's what we want. We want a representative sample for our distribution, right? So thinking back to the last lecture, we want to imagine this first line here being in green, as it was there, and we say the accuracy of the Monte Carlo increases as the size of the sample increases, right? Because the sample becomes more representative as it gets larger, right? Now that is because it's a random sample. A sample doesn't automatically become more representative as it becomes larger. If we think back to that example of US voters and a poll where they asked people only in one neighborhood who they were going to vote for and were not going to get the right outcome, if they made a bigger sample and just continued asking people in that same neighborhood who they're going to vote for, their sample would still not be representative as it got larger. But a random sample does tend to get more representative as it gets larger. So let's do a quick experiment with generating a sample from the standard normal distribution and evaluate whether it's representative. Okay, so here is creating a sample of size 25. Standard normal distribution is where the mean is 0 and the standard deviation is 1. This first column is our uniform values between 0 and 1. And let's see, we will reflect them through the curve and down. So this 0.4 will come through over here and down and be a little less than 0 or minus 0.2. This value here, the higher one of 0.924, comes over and down to about 1.5, 1.429. So the rest of these blue values are the rest of these probabilities coming over to the curve and down. So this last column is 25 values from the standard normal distribution. Right here I have a histogram and then a computation of the mean and the standard deviation of my sample. Mean is minus 0.04, standard deviation is 0.74. I was looking for a mean of 0 and a standard deviation of 1. And if we look at the histogram, we would probably agree that that histogram is not at all a good replacement for that probability distribution, right? So I would say the sample size here is not adequate and we need a much bigger one. So here are some larger samples. Right? So when asking how large a sample, we can also ask that as how many iterations or realizations. So in a Monte Carlo simulation, there's various words you can use, and I've been saying a sample of a given size, but we can also call those sample members iterations, or we can call them realizations. Right? So here's some larger samples. Sample of size 100 is doing a pretty good job of getting the middle of the distribution right and giving us an idea of the spread. Sample of size 1,000 is doing a good job on the spread, and it's starting to fill in the tails. The sample of size 10,000 is actually now doing a much better job of filling in the tails, right? And depending on how far out those tails we need to go might define how big our sample needed to be. But we can see that a sample that's larger is definitely much more representative than a sample that's smaller. Right? So we say our input sample is large enough when it adequately reproduces the probability distribution, but now we're seeing that how large it needs to be kind of depends on what we need to know about the output distribution. So let's instead take this from the direction of the output sample. The output sample, which of course is exactly the same size as the input sample, the output sample is large enough when the statistics of interest stabilize, right, and stop changing with each new sample member within delta. So the statistics of interest are going to be, do we want to know the middle or do we need to know the tails? And when the statistics of interest stabilize, that implies that we're not just going to decide on how big a sample and generate the sample in advance. It implies that we're going to generate the sample one member at a time, and for each new member of the sample, evaluate the statistic of interest, and each time see how much it's changed from the last, and if it's still changing more than delta, then generate another member of the sample, right? And when the statistics of interest stabilize, this is called convergence. Okay, so how much is enough? We continue creating and evaluating new sample members until the statistic of interest stabilizes, then we've reached convergence. So here's a distribution showing two different metrics or statistics. Here's the mean in the middle. Here's a 1% value in the tail. All right, we don't usually look at a 1% damage, but we sometimes look at a 1% stage. So let's go ahead and still see this as an example. Let's start with a small sample. For 100 sample members, here's our sample mean, and it is stabilizing within 100 members. But if we look at our 1% exceedance computation, this is not at all stabilizing with our 100 sample members. And note this vertical axis is not the same here and here. This sample mean is going to appear down here on this figure. So for the 1% exceedance value, clearly we need a larger sample. So let's extend that out to 1,000 members. Right? Now my 1% exceedance value is starting to stabilize, right? So for the metric of a value out in the tails, I'm going to need a much larger sample than if I was only interested in the mean. Now we saw something similar to this in the previous lecture where we simulated rolls of 2 dice and considered the likelihood of the sum. And in fact, consider the likelihood that the sum was 7. And we continued adding new rolls and computing the estimated probability of rolling a 7 again and again with each roll, and watched until that probability stabilized to what we knew was the true value, which was 1 in 6. In that case, we were generating the input sample, right? So we knew when it had stabilized to the right answer because we knew the right answer, which is a probability of 1 in 6, to get a 7 as the sum of 2 dice. In this case, we don't know the value that we're converging to because we're looking at the output sample. Right? So we don't know that we've converged on the right value. We only know whether or not we've converged. But if we have reached a true convergence, then it will be converged onto the proper value. All right, so now let's look at 2 key questions, right, to see, to kind of tie together the ideas. So the first is, why do we need Monte Carlo? All right, why are we talking about this in this lecture about EAD? Right, well, when we include uncertainty in our 3 summary relationships for computing EAD, then Monte Carlo is an effective way of computing the probability distribution of EAD that reflects those uncertainties. Okay, so the next question would be, well, why do we need to include the uncertainty in the estimates of those various curves? And the reason is something called the flaw of averages. EAD is a nonlinear function of those other random variables. And so that means that well, what happens with a nonlinear function is that the function evaluated at the expected value is not going to be equal to the expected value or best estimate of the function. Now, there used to be a slide that showed a linear and a nonlinear function, and how for the nonlinear function, the evaluation at the best estimate was not the same as the best estimate of the curve. This time, we're going to jump right to the cartoon. Right? This is a cartoon by a guy named Sam Savage, and it shows a version of the flaw of averages. What we have here is a drunk guy who's trying to walk down the highway, and he's attempting to walk down the center of the highway, right? But he's drunk. And so he's staggering from one side to the other, veering into one lane of traffic, veering into the other lane of traffic. We've got to see a truck coming in this direction. There's probably, unless there's traffic behind us, there's probably some cars coming in this direction. right? So our X variable is the position of this drunk guy in the road. And the expected value of X is the center line, right? His average position is the center line because he's actually attempting to walk down the center line, even though he's fairly often not on it, right? So the expected value is the center line. Our function is the state of the drunk. Is he upright or has he been flattened by traffic, right? So if we evaluate that function at our expected value of the center line, then we're going to come to the conclusion that he's fine, right? He's in the middle. He's not going to get hit. He's good. But if instead we consider the expected value of the function, considering any location that he might be, then in fact our expected value of the function is that he's been flattened by this truck or some car, right? So the moral of this cartoon is that sometimes the consequences of diverging from the mean are large and have to be represented in the analysis. We had to capture the fact that he's not really usually on the center line, right? So it's a bit gruesome, but it captures the idea of the law of averages kind of nicely. So that was Monte Carlo simulation. And if you have questions about any of those slides, please go to the discourse site and type them in. I will try to be there real time and answering them as quickly as I can. Next, we're going to talk about the method that FDA uses Monte Carlo simulation, which is a method called curve sampling. And it's a little different than the example that we looked at here. Right? So that's the end of this video, and I'll see you in the next.